Hey everyone, we're going to talk today about active and passive transport, one of the important cellular processes that you need to know. So first of all, what's the difference between active and passive? So active means you're high energy, right? You're very, very active. Whereas passive, you're kind of like a couch potato, right? You're just kind of vegging out, watching things happen. And so one requires a lot of energy and one just happens on its own regardless of what you do. So that's kind of the difference between active and passive transport. And so what I want to focus on today is talking to you about passive transport. And there's two particular types of passive transport that you need to know about. And one is diffusion, and the second one is osmosis. And so let's talk about diffusion first. Diffusion is when you have movement of particles from an area of high concentration to low concentration, right? And I say it like that because then you'll remember it, okay? So it doesn't matter what it is. This is a natural movement, a natural state of things. For instance, if I were to take some colored food dye and drop it into a glass of water, you would have a very, very concentrated bit of food dye in part of that water. But eventually you'd watch over time and that concentrated food dye would start to spread out. It would get diluted as it moved through the water, but it would spread out more and more and more over time until it was completely filling the glass, making the glass reflect the color that you put in there, right? So again, the concentrated area, the high concentration, moving outward and upward and downward throughout the glass, filling up in and out between the water molecules to low concentration. And that's diffusion. Another example, if I sprayed perfume, my imaginary perfume bottle in this room, it's going to spread throughout the room, and these molecules will find their way from where I first sprayed it, the high concentration, to filling outward the low concentration. And eventually, depending on who was closest to me, they would smell it first, and so on and so forth, and the people furthest away would smell it last, but eventually everyone would smell that. And so this is a natural process. It happens because molecules move. Molecules are jumping around all the time. Sometimes they're really tightly packed, like in a solid, and sometimes in a liquid, they're moving a little bit more, and then in a gas, they're moving really, really fast. But the point is when they're moving and shaking and everything else, they're bouncing into each other, and every time they bounce, they move apart. So it just makes sense that if you have a high concentration of stuff and you're bouncing and moving, that you're eventually just going to keep bouncing further and further out until you fill up space. So that's kind of the science behind why diffusion happens. So in any case, let's talk about what osmosis is. So osmosis is a particular case of diffusion involving water across a semi-permeable membrane. Now, a membrane being permeable means it allows things to get through. There's like holes in it, okay? If something's completely permeable, everything just gets through. Permeable is kind of like just a giant hole. But semi-permeable means some things can get through and some things can't. A really good example of that would be if you were using a fishing net, trying to catch fish. Maybe you were at the beach trying to catch those minnows in a fishing net. We've all done that as kids at one point or another. And so your goal is to catch the fish in the net. The fish can't get through the net, but the water, sand, shells, everything else does get through the net. So it's semi-permeable, permeable to the water as you're moving the net through the water, permeable to the sand and the shells, but not permeable to the fish. The fish will get stuck in the net, okay? So let's show an example of osmosis in a minute, but first I just want to go over diffusion one more time. So here's some pictures. I want to point them out. So you have a high concentration of material, and over time that high concentration, because it's bumping back and forth, will eventually bump to this side of this area where there's no concentration until you finally get both sides equal. Now, when you get both sides equal, we call this a state of equilibrium. Notice the word equal is an equilibrium. That means both sides are equal. So just like in math, 4 plus 1 equals 5. 4 plus 1 and 5 are the same values. They are equal. And so here we've achieved equilibrium. Now, it doesn't mean that once this happened, these things just stop. certainly molecules are still bouncing around, they're still hitting off of each other, but what's happening is the molecules are bouncing this way at the same rate they're bouncing that way, right? So the numbers are always fairly the same. You know, over the course of time, law of averages, those kinds of things, laws of probability, right? So now let's take a look at osmosis, in particular with the semi-permeable membrane. So if you take a look here, you've got water, and water's the pink stuff, and the pink stuff, if you look, this red dotted line represents a semi-permeable membrane. And so if you look, there are holes between these red dots. So if you look very carefully, the pink liquid, the water, can easily go through this semi-permeable membrane. However, these molecules cannot, okay? They can't get through. They're stuck on their respective sides. So when I look at this, I can see that I have a higher concentration here of particulates, and I have a lower concentration of here. Now, what that means is the percentage of water is less on this side. So if you think of that of 100%, and I'm going to make up numbers here just to give you some mathematical concepts to think about, but let's say that this is 75% sugar, and that means that the other part of this solution, this pink liquid, which we're going to say is water, is 25%. Well, if this is 75% of particulates here, this has got to be much less than 70%. Let's give this a number like 25%. That means that there's 25% of sugar molecules in this whole mixture here. That means there's 75% water. So I've got 75% water here. I've only got 25% water here. That means that over time, the water is going to move across this membrane until we're in equilibrium, where the water, let's say, is at a 50-50 ratio. Because the concentration of water was so much less over here, it required a lot of water to move across to bring this level up. And that's what happens with osmosis. So what's the real world implications? The real world implications is that if you have a lot of solute outside a cell, and this is examples of blood cells, if you have a lot of solutes, right, a lot of salt, a lot of sugar in solution outside the cells, and it's a semi-permeable membrane where the salt or sugar can't rush into the cell, it means that you're going to have a higher concentration of water inside the cells, and the water is going to rush out in a hypertonic solution, and the cell will shrink. So just like we had here in this example, you can imagine this side being the cell, and so the water will rush out to this side where you have that hypertonic solution. In an isotonic, you have equal amounts of solute on both sides of the cell, and this is the state that cells like to live in, because the amount of water going in equals the amount of water out. Isotonic, we're in equilibrium. The other way is that if you have a hypotonic solution, that means you have very little solute outside the cell. So in this case, if you had very little solute outside the cell, and this was the cell this time, okay, it means that the solution's going to rush out of the cell, into the cell. So if this is the concentration outside the cell and this is the inside of a cell, what's going to happen is you're going to get water rushing in. And so that's a hypotonic solution, very little solute outside the cell. It means water rushes into the cells, fills them with water, and can even cause them to burst if it's hypotonic enough. So that's it on osmosis and diffusion. Hope you found that helpful.